All right, peeps, here we go. 4-5, planes and lines. We're also going to do 4-6, so buckle in. This will be a slightly longer video, but we get 2 for the price of 1. Hurrah. All right, this first stuff, pretty basic stuff. What is a plane? A plane is a surface. So think of your desk, your ceiling, your wall. It's two-dimensional. It is, as we say, boundless in 2 directions. All right. So we're going to use a phrase like coplanar. Again, should be fairly straightforward. That's on the same plane. Example, the points on each face of a cube, right? They are coplanar, those 2 red dots. And as you might expect, non-coplanar means they're not on the same plane. For example, you and the ceiling are non-coplanar, unless, of course, you happen to be currently reversed your gravity and you are now lying on the ceiling. Transversal. Here's where it gets a little tricky. This is new. It is a line that intersects, right, meets up with 2 coplanar lines. So here's an example. So there's 2 lines which are coplanar. They're both on the same plane. Any line that, by the way, you draw on your paper obviously is going to be coplanar. And that line there intersects them, both of them. So that line is coplanar. Sorry, is a transversal. Next, we have some phrases that we're going to use. Alternate interior angles, alternate exterior angles, corresponding. We should add to this same side. And that can be same side interior or exterior. All right, what is alternate interior? They're on the inside, they're on the inside, but they are opposite each other. And that'll become clear in just a moment what I mean by inside, okay? Alternate exterior, same thing, outside, but opposite. Corresponding, the same relative position. So we are describing the relationship between 2 sets of angles in transversal angles. Okay, so let's look at some transversal angles here. All right, angle 1 and 6. You don't need to write this one down, but hopefully you can see that angle 1 and 6 are what we call vertical angles, right? That's kind of a review. If I look at angles 2 and 6, they're not congruent. They're supplementary. We call those obviously supplementary, or they form a linear pair. All right? So again, vertical angles, angle 2 and 6 are supplementary. But angles 6 and 3, let's highlight those 2. So here's 6, here's 3. Notice they don't share a vertex any longer, right? They're in different neighborhoods. If you think about this is a neighborhood and this is a neighborhood, right? So what we can do is we call angles 6 and 3, they're on the inside of the 2 lines, but they're opposite the transversal, right? They're inside, sorry about that. They're inside the 2 lines, and then they're opposite sides of this transversal. So we call those AIA, alternate interior angles. Now, angles 4 and 5. So here's 5, here's 4. Notice in terms of the neighborhoods, they're on the outside. And again, they're alternate. So as you might expect, those are alternate exterior angles. And then corresponding angles, these are somewhat tricky, but they're in the same relative position. So if I look at angle 5 and I say what's in the same position as 5, not in this neighborhood, but in this neighborhood of circles, of angles, then I would say Angle 7 is in the same position, right? Because I can take this angle and put it on top of that one. It's in the same quadrant, same region. Okay, so I think I said, for example, list all the corresponding angles. Well, 5 and 7 are corresponding. Angle 1 and 3 are corresponding. Angle 6, shouldn't really use that angle marker, but angle 6 and angle 8 are corresponding, and 2 and 4 are corresponding. Make sense? All right. So those phrases are important. Same side, what does that mean? Same side interior, same side exterior. That should be fairly obvious. 6 and 7 are on the same side, but on the interior. All right? And likewise, same side exterior, 5 and 8. All right. When two lines are parallel. Now notice these two transversals, N and M, appear to be parallel. And they actually will tell you by drawing a little arrow. And they typically turn it into like a little triangle. And they face the same way. And sometimes they will have two sets of parallel lines, in which case one will have a double parallel. All right? Just means that they're headed the same direction. All right. So if these two lines are parallel, then angle 2, this angle here, right, is the same as angle 6, right? It's also the same as, if I can spin this around carefully, angle 7. So I'm going to jot that down. Angle 2 and 6 are congruent, and angle 7 is also congruent to it. Now we also know that the vertical angle, angle 3, is also congruent to that one. All right? Notice then you can talk about the alternate exterior angles being congruent, right? Or you could say, for example, angle 3 and angle 6, alternate interior angles being congruent. When the lines are parallel. If the lines aren't parallel, then we don't know that those angles are congruent. So angle 5, we can see, has to be congruent to angle 4. It also is congruent to angle 8 because of vertical angles. And then angle 1. All right? So we've got these neat little relationships going on when we have parallel lines cut by a transversal. What are parallel lines? Well, they're on the same plane, but they don't intersect. Why? Because they're headed the same direction. And they're not the same line. So there's an example there. Again, we show that they're parallel by putting a little arrow in the middle of them. That kind of tells you it's, not only do they look parallel, but they are parallel. All right? Even in a scenario like this, you go, no, those lines aren't parallel. Why, yes, they could be. And for those of you who are saying like, what, Mr. Larson? Those lines look like they would meet. Well, let me add a few details to this image, and maybe you can see how these lines could be parallel lines. Okay, so we can see like fence posts, right? And the road and those two lines, which would be going off together in what we call the vanishing point. So they could be construed as parallel. They won't be doing that typically. The lines will look parallel to you, all right? Skew. Let's go back to the die for a second. Skew lines, yeah? So we got a 2 there, we got a 1 there, we got a 3 sitting on this side. Skew lines are two lines that are not coplanar. Okay, so they're like parallel in that they don't meet, but they're not on the same plane, and parallel lines are on the same plane. So here I've got a red line in the front yes? And there I've got a blue line, or a green line in the back, and they don't intersect. And they're not on the same plane. All right, 4, 6. 2 notes in one, remember? All right. This is all about the angle of lines. And the magic word is slope. So this should all be review from algebra class. Rise over the run. Remember that? I'm going to skip to this one, y2 minus y1, and then x2 minus x1. And I know I wrote it differently from what I said, and I did that on purpose because you have to recognize that whether you subtract the second coordinates from the first coordinates or the first coordinates from the second coordinates, it doesn't matter. We get the same slope. This probably was not introduced to you. It's called delta y over delta x, and delta means the change in the y's and the change in the x's. And finally, if your slopes represent different quantities, yeah, like miles per hour, right? Miles per hour. And if you change the miles and change the hour, that's, you know, a new rate, right? That's a slope. So higher mathematics tends to look at slope in terms of rate. All right. This, again, is review. You know, this is a positive slope. This is a negative slope. And this is a 0 slope. And this is a no slope. Okay? Why? Because it's vertical. There is no highest number. Okay? So there is no slope here. And that's the null set symbol for nothing. Parallel lines. Going super fast here. The slope of this line, if I compare it to the slope of this line here, yes? M1 and M2 will be the same. Now, if I have two perpendicular lines, lines which are meeting at 90 degrees, they have to equal, the product has to equal -1. So this tells you that there are opposite reciprocals of each other. An example of that is over here. So on my black line, I have a slope of, well, we can see here, I have a slope of going up 1/3, right? And then if I look at my blue line, I have a slope of going down 3/1, right? All right. So you can see that if you multiply 1/3 times -3/1, you get -1. And that's how we know that lines are perpendicular on a graph if we multiply them. So questions are going to come at you like, ooh, is this a right triangle? Well, it looks like a right triangle. It's not marked by a right triangle. Well, I can use my coordinates here to establish that, right? Namely, I'm going to check, how does this line's slope compare to this line's slope? So what do we do? Well, find the slope. So the slope of what we would call FE. So I usually do an M and then I put an FE kind of lower as a subscript next to it. And the slope of FE would be, again, order doesn't matter as long as you're consistent. So I'm going 7 minus 4 and then 4 minus 8. So I get 3/-4. My slope of FC then is, and again, subtract however you want, but remember, make sure that you always start with the y's. I like that to be a positive number, so I go 7 minus 3, and then 4 minus 1, and I get 4/3. Well, if I compare these two, they're definitely not the same. They're opposite reciprocals. So this can be answered with yes, because -3/4 times 4/3 is -1. All right, there we go. Best of luck as you work through those problems in sections 4, 5, and 4, 6.